In this video, we're going to understand LeetCode problem 840, magic squares in grid. This problem combines matrix traversal, pattern checking, and a bit of math logic. Let's break it down step by step. A 3x3 magic square is a grid that uses all distinct numbers from 1 to 9, exactly once, such that every row, every column, and both diagonals add up to the same sum. You are given a grid of integers with row times column dimensions. Your task is to determine how many 3x3 subgrids inside this grid are magic squares. Keep in mind, a valid magic square must contain all numbers from 1 through 9 with no repeats. Even though a magic square is restricted to numbers 1 to 9, the given grid itself may contain numbers up to 15. You must check every possible 3x3 subgrid within the larger grid. The final answer should be the count of all valid 3x3 magic squares found in the grid. Let's understand this problem using example 1, exactly as shown on the screen. We are given the grid 4, 3, 8, 4, 9, 5, 1, 9, 2, 7, 6, 2. Our goal is to find how many 3x3 subgrids are magic squares. First, look at the top left 3x3 subgrid, highlighted in the image. This subgrid contains all numbers from 1 to 9 exactly once. Now check the sums. Each row adds up to 15. Each column adds up to 15. Both diagonals also add up to 15. Since all conditions are satisfied, this is a valid 3x3 magic square. Now look at the next 3x3 subgrid, shown below it in the image. Even though it contains numbers from 1 to 9, the row, column, and diagonal sums are not equal. Because of that, this subgrid is not a magic square. So when we scan the entire grid, one subgrid is a valid magic square. The other one is not. That's why the final answer is 1. Now look at example 2. Input grid is 8. Since the grid is smaller than 3x3, it's impossible to form a magic square. So the output here is 0. Final takeaway. We slide a 3x3 window across the grid, check each subgrid carefully, and count only those that satisfy all magic square rules. Let's break down how this solution works step by step. We are asked to count how many 3x3 magic squares exist inside a given grid. A magic square must follow 3 strict rules. First, the square must contain all numbers from 1 to 9 exactly once. Second, every row and every column must sum to 15. And finally, both diagonals must also sum to 15. Step 1. Why do we scan only 3x3 subgrids? A magic square is always exactly 3x3. So instead of checking the entire grid at once, we slide a 3x3 window across the grid. Each valid 3x3 window has a center cell, and we use that center to validate the entire square. Step 2. Optimization. Why check center equals 5? Here is a key mathematical property. Every valid 3x3 magic square using numbers 1 to 9 must have 5 in the center. So before doing any heavy checks, we immediately skip any subgrid whose center is not 5. This removes most invalid cases instantly and makes the solution efficient. Step 3. Validating numbers and uniqueness. Inside the helper function, we traverse all 9 cells of the 3x3 grid. Ensure each number is between 1 and 9. Track whether each number appears only once. If any number is repeated or missing, the square is rejected. Step 4. Checking row and column sums. As we scan the grid, we calculate sum of each row, sum of each column. Every sum must be exactly 15. If even one row or column fails, it's not a magic square. Step 5. Checking both diagonals. Finally, we verify both diagonals. Top left to bottom right. Bottom left to top right. Instead of summing all 3 values, we use a shortcut. Each diagonal must add up to 10 excluding the center 5. If both diagonals satisfy this, the square is valid. Step 6. Counting all valid magic squares. We repeat this process for every possible 3x3 center in the grid. Each valid square increases our count by 1. And that's how we efficiently find the answer. Alright, logic is ready. Let's hit run and test this against the sample input. Perfect. The output matches exactly. Now let's submit. And yes. Accepted on the first try. Clean logic, optimized checks, and zero extra space.